the impacts of deforestation, you can feel the impacts on the local climate. You lose this capacity to regulate. In Northern Australia, I've witnessed the extensive dieback of mangroves. That is much larger than it has been in the past. You start getting a cumulative effect. With this climatic change that we're seeing in these extreme events, that is going to have a very dramatic impact on ecosystems in the future, and it already is. Things are changing all the time. You might not see it because it happens often over a very long period of time. So that's where the satellite record is so great, because you can pick these things up. An increasing number and diversity of satellites have been launched. We can use that information to understand how the land surface has changed. This record is increasing. It becomes more valuable as time goes on. Where else do you have a permanent record of what's been happening? That's it, really, at a global scale. You can start to look at how the climate is interacting with what's happening on the land surface, where the greenhouse gases are coming from deforestation, agriculture, urbanization, and it gives you that connection between what's happening and what we're seeing in the atmosphere. The CCI program has been fantastic in the way that it has brought together different components of the Earth system, and I think that's the way forward. You have to treat the system as a complete whole, look at all the interactions, the feedback, understand it, make sure that what you've got is correct, and then be able to then understand what the future might be through effective modelling. You need that long time series. You need to look at these cross links. You need to have the ability to reanalyze this data, so we need to make sure that we do have the resources to push that forward. In varying ways, the ESA CCI feeds into the IPCC and other elements linked to the United Nations Framework Convention on Climate Change. CCI Biomass is focusing on generating global maps of the amount of carbon in forests around the world. And this information is really used to help to validate some of the global climate models. This ability to collaborate on a global scale is fundamental. All the time, climate is changing, so it's almost like a race. We need to address, first of all, measuring it, assessing the uncertainty, make sure we're happy with it, and then feeding that into policy, and that takes time, but we don't have time. I've experienced many of the world's environments, and what I've witnessed quite dramatically is that those changes are perceptibly happening really quickly now. The satellite record over the last 30 or 40 years has captured these changes in fantastic detail. This information is really critical for us to make the future decisions about mankind, but also the biodiversity and the whole function of life on Earth. We know it's happening, we know it's there, and we need to be much faster at reacting to make much more rapid decisions that are informed and are based on solid science. The pace of the change is almost faster than the science that we can do to understand it. There needs to be this capacity to respond urgently. What happens in 50 years' time? Will this landscape still be sinking in carbon? Maybe the tree species may respond differently to climate. Maybe you've got different biodiversity here, different pollinators, things are changing. We need to be able to understand the direction of change, how quickly it would be, and the magnitude of it in a way that is useful for future generations. To create this pathway that addresses the problems of today and takes into a really positive future for both ourselves but all the future generations of decades or centuries to come. What we do now is critical to that future. We have to proactively do something about how we use the land, how we treat the environment, and how we can really work together with nature to support life in general. It can be done.
Glaciers in every corner of our planet are retreating. It depends where you are, how quickly that's happening. But even in the polar regions, it's happening much quicker than we expected. But in alpine regions, the glaciers that are there today, most of them won't be there in 50 years' time. And unfortunately, the pace of retreat is quickening too. So on average, Antarctica and Greenland are losing 5 to 6 times more ice today than they were losing in the 1990s. It's just increasing every year. And in total, Earth is losing about 1 trillion tons of ice every year. and that's not being replenished. It just goes into the oceans, causes sea levels to rise, changes the salinity of the oceans, and it also changes patterns of ocean circulation, disturbs the atmosphere and the weather patterns around the planet, and it's something we're going to have to adapt to. This feature was created when the ice sheet in Britain was melting away, and that took about 50,000 years in total to retreat across the British landscape from northern England up into Scotland. And that gives us an indication of how fast ice should be retreating in a glacial period. When we look at the changes we see today in Antarctica, it's happening about 100 times faster than that, and that's way too fast. And that's not normal, that's not something that they can withstand for another century or two. It's going to cause changes for the future. That's why it's really important to monitor the polar regions from space today and check whether the retreat is as we expected. There's been a step change in people's appreciation of how the ice sheets respond to climate change. In the first two IPCC assessment reports, it was understood that Greenland and Antarctica wouldn't really react to climate change. And we now know, thanks largely to satellite observations, that that's not the case, that the ice is melting really rapidly. What's been absolutely essential is long-term satellite measurement programs. ESA's Climate Change Initiative is a really powerful program. ESA are really driving the launch of Earth observation satellites to study our planet, and it makes use primarily of their measurements that have been collected since the early 1990s now. So we have just about 3 full decades of observations, and we can go back to those earlier missions as well and check measurements to see how the ice sheets have changed over decades, which gives us more confidence to tell people that these changes aren't just a short-term variation and they're a pattern that's progressively changing and will continue to change in the future. So this is climate warming, it's not weather. But it takes a long time to get things into space, and not just to design them, but actually to then build them. It's a slow process and it requires continuous investment. Climate models and satellites in space looking at Earth, they're the cornerstone of what we've learned in 20 or 30 years. Those of us that have worked with satellite measurements have had to invent new ways to interpret them to study the planet. You have to go on the ground and check that what you think is a real measurement is actually a real measurement, and that's why we make routine field campaigns. There are some places that we have to return to year on year. We use them as reference sources, and when that's in the cryosphere, you get to see the landscape evolve throughout your own career. And Iceland's a really good example of that. There are glacier systems in Iceland that I visited 25 years ago that look very different today, and that's the real pace of climate warming and how it affects ice at low latitudes. The progressive retreat of the polar ice is really now unarguable in the satellite record. We've developed different satellite techniques to study each part of the cryosphere, and we can now confidently map them all from space. Unfortunately, the satellite record shows every corner of the planet is losing ice, and that can't be a consequence of slow glacial retreat. It's climate change. The ice sheets have switched from a position of being a slumbering giant throughout most of the last glacial period to reacting really rapidly to what we might think are small changes in the planet's temperature. So half a degree centigrade warming completely destabilizes parts of Antarctica and Greenland. By the end of the century, we expect 400 million people around the planet to get flooded once each year as a consequence of the sea level rise that we're really bought into already. The challenge now is to give people some hope that there's a chance to arrest those changes and adapt to them.
Always been astronauts and cosmonauts living and working on board.
Umberto Guidoni, an Italian astronaut representing the European Space Agency.
On the 19th of April 2001, Italian ESA astronaut Umberto Guidoni became the first European astronaut to visit the ISS.
We have booster ignition and liftoff of the Space Shuttle Endeavour, extending the reach of the space station.
His mission included helping to install the Canadian robotic arm and transferring scientific equipment and experiments. Back then, the ISS consisted of just a few modules. Today, the station is more than 100 metres long, and the area for living and working is larger than a 6-bedroom house, with 2 bathrooms, a gym, and even a bay window with an unsurpassed view. In 2009, Frank de Vin became the first European commander of the ISS.
We have learned an awful lot in these 20 years of the International Space Station. How to build the biggest infrastructure, technological infrastructure in space that has ever been built. How to do science, how to do operations sustainably for 20 years with humans in space.
Over that time, this microgravity laboratory has hosted more than 3,000 scientific experiments. With benefits to Earth and future space exploration, research ranges from studies in materials science and pharmaceuticals to investigations of plant growth and even asteroid mining. With most astronauts spending 6 months on the station, scientists also have a better understanding of how humans adjust physically to microgravity and mentally to the challenges of isolation far away from home.
The International Space Station provides an environment where scientists can continually study how humans adapt to space. We have engineers and scientists working together to understand how materials adapt in the space environment. And all this information is going to be critical if you're going to be very far from Earth without any chance of bringing things with you, and you have to be completely self-sufficient on a mission and perhaps future habitation on other planets far away from Earth.
ESA is working with its international partners on Gateway, a new space station in orbit around the Moon. Future plans for human exploration include landing astronauts on the lunar habitat, before eventually following our robot pioneers on a crewed mission to Mars. All these ambitions build on the knowledge acquired over more than 20 years of building and operating the ISS.
And that is yet to come, because as of now, we will have permanently 7 people on board of the International Space Station. We will have much more crew time available to do science and technology. A lot of companies now are interested and fly their own research to the ISS.
Almost exactly 20 years after Umberto's mission, ESA astronaut Thomas Pesquet is preparing to launch to the ISS. He'll be followed later this year by Matthias Maurer. These missions will add to our knowledge of science and long-duration spaceflight as humans venture further from Earth.
Our main task was to install Canadarm2, a space crane needed to complete the construction of the ISS. In addition, the Space Shuttle Endeavour was carrying supplies for the station's crew. We delivered consumable and scientific experiments thanks to the Raffaello logistic module, a jewel of European technology. Working on board the ISS, I felt I was making a small contribution to building humanity's first outpost in space. The spirit of international collaboration was well represented by our diverse crew, made up of 4 Americans, a Canadian, a Russian, and myself, a European with an Italian flag. We should be proud of more than 2 decades of human presence in orbit, for the scientific and technological achievements, but above all because up there, a small group of men and women have proved what we could achieve by working together for the progress of humankind. It is the most important lesson of the ISS project, especially significant in this difficult time for the planet.
It's hard to believe that it's already 20 years ago since our dear colleague Umberto Guidoni was floating through the hatch of the shuttle and entered the International Space Station as the first European. So much has happened since then, so much successes, but also lots of challenges. If I counted correctly, 17 European astronauts have flown to the ISS since then. Myself, I was number 8 in row, the first European long-term flight in 2006. The station was much smaller then, and today it's such a huge structure in low Earth orbit, which gives a permanent home to 7 astronauts. I'm so proud on our achievements in Europe and together with our international partners.
If you're 40 years old or younger, more than half of your life, a human has lived on the ISS at any time. That's an amazing achievement. So if I could think of one property of this fantastic machine that I could pick out, then I would say the ISS is the most improbable machine that humanity has ever built. We all know there's a lot of science going on, and it's very important for us down here on Earth to get those science data, but we rarely look at what an achievement it was to actually build that machine. The modules, such as the ones that you see behind me, were actually built on 4 different continents and were launched individually on rockets into orbit at 28,000 kilometers an hour, where they have been put together. And they had to fit with a precision more than the hundredths of a millimeter together, but they've never been tested on Earth if they fit together. That's how sure engineers were that this machine would work. That's what an achievement it was, to put this machine together in space, working together across the globe. So you see from this fantastic achievement that international cooperation is the key. If you try to do things alone, you can only get so far. If you work together with other countries, you can achieve things that one nation could never achieve alone. Plus, it forces you to work together in peace. So that's an achievement alone that I think is already worth the celebration of today. Happy birthday, ISS.
I really had an overwhelming feeling of awe for the technology that we were using there. I still remember the first time we opened the hatch, the clean air, the sense of being in a building instead of just being in a tiny spacecraft. The ISS then, and much more now, gives us the feeling of something permanent, that this is something in which we are actually building a permanent science laboratory in space, and being there is really overwhelming from the point of view of the enormous space that we have, the level of technology that we're using, the technology and the displayed also in the science experiments. It was really the highlight of my life, and probably of anyone's life that actually gets there.
My favorite memory when I was on the Mir space station was actually when I was on the Soyuz spacecraft before docking on the space station, and we were about 20 kilometers away from the space station, and I saw the space station on the right side from my window. We were at the Terminator, so everything there is gold light, and I saw the space station floating in the sky or in the space. And it was a gold color, so I had this very strong memory for all my life.
Probably my most vivid memory of space station is when I saw it for the very first time. We were approaching station, going in towards docking in our Soyuz, our spacecraft, and I had not seen it with my eyes yet. I'd seen it on the camera, on the periscope, but I wanted to see it with my own eyes. The space station that I had trained for so long had been in the center of my thoughts for years, and I wanted to see it. And so I had been told that when you get to about 40 meters out, if you look out of the side window, you're gonna catch a glimpse of it. And so I did, and it was overwhelming. I basically caught a glimpse of these solar arrays, and I knew in my mind how big they are, but it's different when you see those gigantic arrays out there, and they're so beautiful. And it was a very special moment, that those few seconds when the sun is very low on the horizon, it's about to set, and it basically flooded space station with this orange glow, and the solar arrays, they looked ablaze. It was just amazing.
From space, we see the Earth as a spaceship. It is limited in size, it is isolated, far from anything else. It is unique, nothing else resembles the Earth. It is alone in the black background of the universe. And we realize we all humans feel and are as crew members. We are crew members of Spaceship Earth. And then we make the parallel between our spaceship and Spaceship Earth. We think that if we manage Earth like we manage our own spaceship, like we manage the space station, for example, where astronauts are the champion of anti-wasting and recycling resources, then Earth would allow humankind to go far in the future and live well. So let's learn how to recycle and save our resources.
I was fascinated by the view of the Earth through the window. Such a beautiful planet, carrying life, but such a fragile and vulnerable one. And it is this new view, full of admiration, respect and responsibility, that all astronauts like to share and return. The ISS, with its multiple laboratories, including the European Columbus module, enables a very broad spectrum of experiment to be carried out at the cutting edge of research and technology. And I admire the progress that has been made during these 20 years of permanent use in life. And I'm so proud of the results. It has provided us with essential innovations for some of our terrestrial challenges, climate change and obviously health issues.
I'll never forget my visit to the space station in 2015. One of the highlights was sitting in Cupola, our window module, and filming blue jets, which are gigantic lightning strikes that shoot upwards out towards space from the top of thunderclouds. And this is an excellent example of new knowledge. This is the first time blue jets were filmed, and already it's given us more insight into thunderstorms and how they impact climate and weather on Earth. So here's to another 20 years of living and working on board the space station in low Earth orbit.
And then, of course, a very vivid memory is that first view from the cupola, this special module, which is very small, but it's made out of windows, and so you have this amazing view from horizon to horizon of the Earth. And the first thing that I saw through the cupola was this glorious sunrise from up there, from space. And you really get spoiled, that view from the cupola is something that, it's amazing. I don't know, you get up every day, or before you go to sleep, or just, when you go to the toilet, which is right next to it, you get that habit of just taking a peek outside and see where are we and what's out there. And there's always something amazing to see, this ever-changing beauty of the planet, with different seasons and different weather patterns, and the mountains, the oceans, deserts, the forests, and that also that feeling of familiarity that you develop over time. You look outside and you kind of know what's coming next. What's the next thing, the next city, the next continent, the next island that's going to appear at the horizon, and you kind of wait for it like an old friend. And in a way, you feel that distant presence of about the humans down there that you are overflying.
In December 2006, I got the wonderful opportunity to visit the International Space Station myself, and I took part in the assembly of the International Space Station, and then again in 2009, two missions, SS-116 and 128. And it was absolutely fabulous to be part of doing this, to be part of building this most fabulous construction humans has built. I was happy and lucky to be able to do a few spacewalks and seeing the Earth floating below. In this case was 360 kilometers below, while outside on the space station. That's an absolutely unforgettable experience. We're building this International Space Station to learn how to build and live in space, but also to learn what we need to know to go further in space. And I'm sure ISS will be used many more years as well.
When I was out to do my spacewalk, it was the personal highlight of my astronaut career. The challenge to control my own little spacecraft as the everlasting task in the background. The assigned tasks which had to be completed, regardless of the unexpected. The little to no room for deviation from the optimal, safest way to proceed. The surprise and joy when we flew over Europe with the clearest sight I ever experienced on board or on ground. The unexpected flight path leading us right over my home area Aachen and Cologne. And our mindful pilot Dex, who instructed me to take a minute to look to the ground when we approached Germany. This sight and my feelings were overwhelming. I needed to call me to order and concentrate on my work.
When I birthed the first Dragon to the International Space Station, I realized I was doing something special. Here I was, a Dutch astronaut from a European Space Agency, working with the Canadian robotic arm, docking an American commercial spacecraft to an International Space Station. Beautiful example how all these technologies and countries came together. Also, when I docked the European ATV to the Russian side, working together with my Russian colleague. That is the most important thing for me for the International Space Station. It's built by all kinds of countries that were fighting each other not so long ago in hot and cold wars, and now building on the biggest technological project there is. A beautiful example how you can cooperate. For me, the International Space Station is a beautiful candidate for a Nobel Peace Prize.
And the next very vivid memory, of course, is opening the hatch and floating through, hugging our bodies. That almost unreal experience of flying to space and meeting other human beings who are there to hug you, who actually prepared a warm meal for you, who are going to take care of you in a way in this first few weeks in which you are learning as a new flyer. Yes, there's the enjoyment and the excitement. You're floating, you have superpowers, you can live in 3 dimensions, everything is effortless. But at the same time, you have to get used to controlling your body in weightlessness, controlling all the things that, have that tendency of wanting to float away from you. And so, your bodies help you out a lot.
One of the privileges that we have while living on orbit is to make the ordinary extraordinary. Even a dinner becomes a chance to go beyond any limitations and any heritage. I remember one dinner where we had my crewmate Jessica Meir of Jewish heritage enjoying Russian and Italian food together with the Russian colleagues, Americans, and Hazza al-Mansouri, who is the first United Arab Emirates astronaut. There are no limitations to what we can do when we want to do extraordinary things. Maybe the challenge for the next 20 years is let's do extraordinary things also on the ground.
On my second mission, I was there for 6 months, and we are here in a mock-up of the Columbus module, where I have spent 6 months doing science and working and living in space. Of course, we did not only work, we also had memorable moments. For example, when we celebrated Halloween on orbit, and when we tried to dress up and try to find things that we could do just to surprise each other. These are also memorable moments, of course, but the most important thing is that for 20 years now, we have been delivering science, technology for the benefit of humankind. So again, the International Space Station, congratulations.
It's incredible to think that this year we're celebrating 20 years of International Space Station occupation. To my mind, the most incredible feat of human engineering, the size of a football pitch, over 400 tons of hardware in low Earth orbit. But it was built as a scientific laboratory, and for that time it's been doing valuable research for the benefit of everybody back on Earth, such as investigations into new drugs, sustainable technology, solar power, renewables, crop growth and water regeneration. But more than that, it's about international collaboration. It couldn't be done by one nation alone, and it just goes to show what we can do when we work together. I had the privilege of living and working on the space station for 6 months, and it was the most incredible time of my life. I hope that many other astronauts in the future get that opportunity too. So good luck, whatever the future may hold.
So hey, as you know, this year we celebrate 20 years of continuous human presence on the ISS, which is an unbelievable achievement. I was lucky enough to be part of the last 10 years of that story, that ongoing story. And to me, what's so special about the ISS is its truly international nature, the international nature of that program. We got people from all over the globe working with the same ideals of space exploration, research, peaceful cooperation, and that makes it, to me, truly unique and special. So congratulations of all the ISS partners on 20 years of success on board the ISS, and here's to an even better future of exploring farther together.
Right now, I'm training for my very first mission to the ISS, and my mission is known as Cosmic Kiss. In autumn 2021, I will launch from Cape Canaveral in the United States of America on a SpaceX Dragon capsule. It is hard to believe, 13 years since I first applied to become an ESA astronaut. My dream now is finally coming true of flying to space. Soon I will be orbiting Earth roughly every 90 minutes, and I will be able to see 16 sunrises and sunsets a day from the cupola window on board of the space station. Of course, I will be very busy performing experiments in all different scientific disciplines, and I cannot wait to play my part in advancing our knowledge for the benefit of our daily life on Earth, as well as for the future of space travel.
And so I very, very much look forward to going back to ISS. It's very different this time. It's a place that I know very well. That's been my home already for half a year, just a few years ago. And it's just this desire, this longing of going back to a place that I have loved, to live again that experience. It's going to be different in many ways, for sure, different vehicle flying there, different people, but I think it will be the same type of camaraderie, that same type of satisfaction also of very, very dense full days when you get a lot of things done. You know, in a week you might do, I don't know, a dozen of experiments that actually represent an accomplishment for teams on the ground who might have worked on that for years, and there you are, just putting the cherry on the cake, you know, delivering the data that they have worked towards for so long.
hopefully in 20 years we will see European astronauts as well as probably other partners walking on the moon, studying the moon, having a permanent presence probably in or around the moon, and who knows, maybe already putting together the spacecraft that will go to Mars, hopefully also with European Space Agency astronauts in there. For that we are choosing a new generation, so I'm hoping that everybody in Europe that has a drive to work in space, that has a drive to be in the forefront of technology and wants to be operational about it and do something about it and be really in the middle of it, applies to our selection for European astronauts. So congratulations to everybody and for the next 20 years.
We're building this International Space Station to learn how to build and live in space, but also to learn what we need to know to go further in space. And I'm sure ISS will be used many more years as well. And right now I want to congratulate everybody who has been involved in this fabulous endeavor to build and construct and live on the International Space Station. 20 years, that's a long time. Congratulations.
Of course, I hope, as most likely all of you, that ISS will remain not only till the end of this decade, but hopefully till the beginning of the next decade, so we can celebrate the 30th anniversary of European astronauts working on board ISS and advancing our knowledge for the benefit of humankind. Now I wish all my colleagues who are about to leave this planet for their missions all the best, success during their stay on board, and a safe return to Earth. Happy anniversary.
Over the next 20 years, space will be the arena for competition and collaboration between national agencies and private companies. We will see a new era of human exploration beyond Earth's orbit, starting with the return of human crew to the Moon after half a century. And the Moon will be just the first step. Human spaceflight is not only important for its scientific and economic values, but also because it concerns the future of our civilization. Humanity has evolved thanks to its ability to explore the unknown, to go beyond the Pillars of Hercules. More than 500 years after Columbus' voyage, we do not remember the details of the discoveries, but we are aware of how that event changed the history of the world. Imagine what the colonization of Mars can represent for our future. Thank you for listening, and ciao.
My personal hope for the future of human spaceflight is that we continue to further develop our international cooperation. By doing so, we will be able to realize sustainable research and exploration in our entire solar system for the benefit of all.
I hope in the next 10-20 years we will all together again fly in space to go further, to go to the moon, on the gateway first, maybe on the surface on the moon next, and maybe in the 30s, 40s, we'll go together to Mars. And as we go further and further, maybe we will answer this fantastic question. Is there life, or has there been life out there somewhere else besides Earth? This is a question I like to have the beginning of an answer before I leave Earth forever.
Lots of famous poets and painters have walked through these alleys of pine trees, but lots of scientists have too. Welcome to Monte Mario, the highest hill in Rome and the seat of the Italian Institute for Astrophysics. That's the perfect location to bring you our new edition of Space Roundup. On the menu today. After the names and faces were finally revealed to the world last November, we'll follow the very first steps of the new astronaut candidates into their new home, the European Astronaut Centre.
These past 5 months have been all about a transition to this new life. It's getting the logistics right so that we can really focus right now on the real work.
I will be talking to you about the launch that got us all excited at ESTEC in the Netherlands. The Jupiter Icy Moons Explorer started its years-long journey to the largest planet in our solar system.
We will also celebrate a birthday. 10 years ago, Europeans were able for the first time to fix a precise location on the map using their own Galileo satellites.
Good afternoon, Marco.
Nice to
see you. Thank you for having us.
We will be meeting with one of the team members who was in the room that day.
And finally, we'll take you to the place to be if you're interested in the weather. Last December, the first of a new generation of weather satellites was successfully launched into space. And a couple of months later, it sent us its very promising first image.
And there is even more to come.
So stay with us. The Grand Palais éphémère in Paris was buzzing with excitement following ESA's Ministerial Council in November last year. Not just because member states had backed ESA's ambition in space with a 17% budget rise, another much-awaited announcement was also made.
Lots of smiles that we're seeing here on the stage. This is our 2022 class of ESA astronauts.
After a marathon year sifting through a record-breaking pool of more than 22,000 applicants, ESA finally introduced the 17 candidates who made it. With backgrounds in engineering, jet piloting, astrophysics or medicine, the new astronauts already have an exceptional range of skills. But going into space will require learning new ones.
In the next few months, the astronauts here in the European Astronaut Centre will go through the basic training. The basic training will give them, for example, basic robotics training. It's not on the SSRMS itself, the robotic arm that is on the space station, but how to understand how do I operate robotic arms in space. They will have basic EVA training, the basics of how do I communicate under an EVA, how do I get into the foot restraints for an EVA, how do I work with connectors in EVA, for example. They will have technical training about our Columbus module, to be a user, to be an operator, to be a specialist on the Columbus module, and they will have also already some start of the science training that they will have. And not to forget, of course, a big part, because that will be, for a lot of them, will be new Russian language training. The first flight for this new class of astronauts will happen in 2026. And after that, we hope that we have a flight every year. So there are 5 new career astronauts selected. So we hope that by 2030, all of them will have had their first mission to space. The reserve astronauts, they stay affiliated with their current organization. They continue to do the job that they are doing now. However, we will invite them here to EAC to update them on the future of human spaceflight programs, on our exploration program, Terra Novae, because of course they are now very well known in their respective countries. They have a lot of invitations to speak, to go to PR events, and we want them to be aware of what ESA stands for, what we are doing in exploration with ESA. On the other hand, we might also use them, their expertise, because they are also very high-level experts for certain tasks that we want to do in ESA.
We want to use the expertise that John has as a subject expert, of course, with the disability that he has, to see what would it take to fly somebody like John to the space station for a fully functional, fully operational mission. Not just for 10 days to float in space, because that is not the purpose of the ESA program. The purpose is, can we use people with a disability as a full-fledged astronaut? And what would it take to do that?
I think that I can bring lots of things to the feasibility study, but I think in particular I can bring inspiration. You know, inspiration that science is for everyone, but inspiration that potentially space is for everyone.
In early April, the 5 career astronauts, still known as candidate astronauts, finally arrived for their first day at their new and very special school, the European Astronaut Center near Cologne in Germany. They had a first tour of the facilities, getting a sense of what awaits them. For example, taking a dip in a 10 meters deep pool where they will train for spacewalks. Their basic training will last for a full year, so they can learn all about space exploration and prepare for a potential mission. Listening to their initial reactions, the year ahead sounds pretty exciting.
Well, I really love learning. I love challenging myself both physically and mentally, so I'm equally happy of every opportunity to learn new skills. I also love going outside of my comfort zone so that I can learn new skills. And I think this year, when we'll be doing our survival training, when we will be learning EVA skills, we will clearly be pushed outside of our comfort zone, and I feel very happy about that.
Until now we had a lot of theoretical classes, a few hands-on as well, but I'm really looking forward to the sessions, to practical sessions where we will put into practice what we have learned. It's really great to feel all this enthusiasm coming from everyone, and I think we all share the enthusiasm towards this endeavor for the next year.
We are now at the Copernican Museum in Montemario, and these globes represent the Earth and the sky as astronomers saw them centuries ago. Did they ever dream that humans would one day fly into space? Well, fiction is now reality, and the next ESA astronaut to fly to the International Space Station is Andreas Mogensen. He's busy these days, training for his second mission in space called Regin. Andreas Mogensen belongs to the generation of astronauts selected some 13 years ago. After his initial training, he was launched into space in 2015, and he spent 10 days on the International Space Station. Now he's getting ready for his first long-duration mission.
This will bring you in the situation of a warming.
Training is taking place all over the world, but we managed to catch up with him during a brief stopover at the European Astronaut Center in Darmstadt, Germany.
I'm here at the European Astronaut Center for my last session of Columbus training at specialist level before I launch to the International Space Station in approximately 6 months. I'm incredibly excited, but there's still a lot of training to go before I'm ready to launch, especially when it comes to the Dragon spacecraft, where I'll be the first European pilot. That's a huge honor and responsibility, but something I'm really looking forward to. I'm excited and ready for my mission. I hope you are too, and are ready to follow along.
And of course, you can follow Andreas on social media to get all the updates on his mission. So this is an amazing orrery from the 18th century, and it represents the solar system, of course, but not all the planets are there because they just hadn't been discovered yet. So you can see the Sun here, the Earth, and the next ESA astronaut to fly in the future might be traveling to here. The Artemis program aims at returning humans to the Moon. At the end of 2022, NASA's giant SLS rocket launched a spacecraft called Orion to fly beyond the Moon and return safely to Earth. And it did. The uncrewed Artemis 1 mission was a clear success. Preparations are now in full swing for the next Artemis missions, and Europeans are contributing in two ways. First, they will provide the European service module that gives air, electricity, water and propulsion to the Orion capsule and their occupants. But ESA also secured free seats on future crewed Artemis missions, and by the end of this decade, a European astronaut will walk on the moon. That's a giant leap for Europe.
Now, history is always in the making in the space sector, and it is surely true for ESA's latest mission to explore Jupiter, the largest planet in the solar system, and 3 of its moons. The mission is called JUICE, and it recently started its years-long journey to the largest planet, Jupiter.
5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage rapide décollage.
On 14th April, a powerful Ariane 5 rocket took to the skies from Kourou in French Guiana. On board, a jewel of technology, beginning a complex 8-year journey to the outer solar system. The JUICE spacecraft is equipped with 10 groundbreaking instruments designed to uncover some of the mysteries of the gas giant planet Jupiter and 3 of its icy moons. This will be key to understanding how these moons evolved and whether they could harbor vast oceans under their surface, a tantalizing hint that conditions for life could exist other than on Earth. Shortly before the liftoff, we met with Manuela Baroni, member of the JUICE team.
The last 8 years, we have been developing our spacecraft. We have been designing, building, and testing it. But even before then, for many years, scientists and engineers, they have been working on the definition of this mission, doing studies, doing feasibilities analysis. So it's almost 20 years from the first idea of going and studying the icy moons of Jupiter to the launch that will happen in a couple of months.
20 years is really quite a long time.
It is.
Yeah, and also when you think about it, really, I mean, the taste of JUICE is very sweet. But for this mission, what is so exciting about it?
There are many reasons to be excited about JUICE, definitely. Well, JUICE, first of all, is the first European-led mission to the Jupiter system. This is something to be very proud about. This is a major achievement for Europe. And then it's also a step forward to the knowledge and the understanding of our universe. Where are we coming from? What will be our future in the solar system? So questions that have been coming with the mankind since the early ages. And JUICE will help answering to these questions.
So, as in every other mission, surely there are challenges that the team has had to overcome before we got to this stage. What are they and how were they able to overcome these challenges?
Indeed, during the development phase, we have faced many technical challenges and human challenges. If I can just mention a few, in Jupiter there is a very high level of radiation, so we had to screen all the electronic units to survive in such an environment, a harsh environment. The spacecraft has to sustain an extreme range of temperature, hot when it will do the flyby of Venus and cold when it will be in the Jupiter system. Then Jupiter is millions of kilometers away. Therefore, the spacecraft has to have a navigation system and a certain level of autonomy that will allow to perform all the operations completely autonomously and recover from possible failure without intervention on Earth. And then last but not least, there is also the human challenge, because we need to ensure a continuity of the knowledge all along the development and the operation of the spacecraft, so the overall life of the mission. So yes, sending a spacecraft to Jupiter is not a walk in the park like we are doing now.
Yeah. And when do we expect to receive the scientific results and the knowledge from this mission?
Well, the spacecraft will reach Jupiter in July 2031. And soon after, all the scientific operation will start and the data will be transmitted to Earth on a regular basis. Therefore, from that moment, the scientists will be able to start and draw conclusion or to start drawing discoveries out of this data. So, relatively soon, once we are in the Jupiter system.
And you can follow the spacecraft almost in real time, thanks to our interactive tool called Where is Juice Now? Just go to our website.
Fushino Space Center, 12 minutes.
Let's get started. Drive safe. In 200 meters, at the roundabout, continue straight.
So we all take it for granted that our phones are giving us the directions when we're traveling or when we are lost, but the technology behind it is actually fairly new. Very recently we celebrated the 10th anniversary of the very first time the Europeans fixed a precise location on a map, and that even marked the birth of Galileo, Europe's very own global navigation satellite system. Vincent tells us more.
And then we declare success.
March 12, 2013 was a huge day for the Galileo team. For the first time, 4 Galileo satellites orbiting the Earth were able to send down their signal to the navigation lab room in the Netherlands, given a precise location for longitude, latitude and altitude, and thus confirming that European navigation system was indeed working.
Good afternoon.
Good afternoon, Marco.
Nice to see you.
Thank you for having us. Thank you.
Welcome to the European Space Agency Navigation Laboratory.
Thank you for having us, Marco.
Marco Falcone was in that same room 10 years ago, working as the head of Galileo system and operations.
In this room, there was our test user receiver. This is the first receiver that computed the positioning. And here you see the main machine interface of this receiver with some analysis software that is showing, we call this a sky plot in technical terms. It's basically showing you the sky and the position, every point is corresponds to a dot in this diagram, and then you see the accuracy. In this case, you are within a radius of 5 meters. And here you see, for instance, these are the codes. This is the full constellation. You see every square corresponds to a satellite. And as you can see, there are 4 that are the 4 we used for doing the position fix. Okay, then if you see nowadays there are 28.
It must have been quite an exhilarating experience for you when you got the signals on the computer screen, right?
Yeah, because you see it working. And imagine I was at the control center the day before. So telling the operators, this is why our job is fantastic. You see what I mean? Yeah. You can really make it, make it happen. Is what is nice in the end of our job.
The future looks quite promising for the Galileo navigation system with the second generation currently in development. What capabilities would they bring to the table this time?
The Galileo second generation development has started because now we are close to reach full operational capability. It's a lifetime more or less of 20 years. So we need now to develop the system for the next 20 years. And the satellites will have a lot of new capabilities, the second generation satellites. Higher power, much higher power, so that you can receive the signal in all conditions. And also another feature important is electric propulsion for orbit raising, because this will allow to reduce launcher's costs. So all in all, in a nutshell, this is a high flexible system. Why flexible? Because it has to provide the services to users for the 20 years to come, and we don't know yet what the users will want in 20 years from now. So it is very important to have this flexibility. And I'm sure the Galileo second generation will be a success.
And maybe even more reliable and accurate navigation for users as well.
The user can already now be able to compute a position of the order of 20 to 30 centimeters with a certain few minutes convergence time. So already the system that is currently in operation is providing very important services, very accurate, very robust. So this is thanks to the flexibility built in the design that we started already 20 years ago.
Indeed, the second generation is quite promising. Thank you so much, Marco, for taking the time to talk to us.
It's a pleasure.
And we wish you all the best for the future.
Thank you.
Thank you.
So we've now reached the Fucino Space Center in the Abruzzo Mountains. With more than 170 antennas, it's one of the largest teleports in the world for civilian use. Some of these antennas pick up signals from Galileo satellites, and some others have been playing a key role in a more recent launch.
That day, the weather at Europe Spaceport in Kourou, French Guiana, was ideal for launching a, well, weather satellite. On 13th of December, an Ariane 5 rocket successfully took into orbit the first of a new generation of groundbreaking satellites. The Meteosat third generation Imager 1 and its 5 successors will provide crucial data not only to help long-term climate monitoring, but also to improve forecasts of severe weather. And that's thanks to innovative instruments, including a novel lightning catcher.
This is a lightning instrument that will serve very much to give us information related to thunderstorms. Very relevant, for example, for civil aviation activities on the Atlantic. And then on top of that, it has an instrument which is a flexible combined instrument that will give us the state of the atmosphere, information that will come every 2.5 minutes compared to what we had in the past. And so with a much increased pace in terms of time range, in terms of resolution, and in terms also of providing information which is more accurate and more advanced to what we had until now.
So we are now in the control room where it all happened during the launch. And Ernesto, you were the man in charge that day, and you and your teams prepared for all kinds of scenarios. Did you get the best one you could have hoped for?
Siamo molto soddisfatti dei risultati di questa attività di lancio di MTG I1. Ci eravamo preparati molto lunga, molto sfidante. Il team ha reagito molto bene, ha eseguito tutte le operazioni previste, ha risolto le anomalie che abbiamo incontrato e alla fine abbiamo rilasciato il satellite ad EUMETSAT nella configurazione attesa.
Okay, and how do you control a satellite like this in the very first phases? What are the critical parts of a launch like this?
Allora, ci sono diverse attività critiche. All'inizio, nella prima orbita, c'è il deployment dei pannelli solari, l'inizializzazione del sistema propulsivo e poi soprattutto le manovre orbitali, che sono quelle per il trasferimento dall'orbita iniziale in cui il satellite è rilasciato dal lanciatore all'orbita geostazionaria.
Ernesto, thank you very much for your time.
Grazie a te.
So this is the antenna that took control of the MTG satellite immediately after it separated from the rocket. And recently it's a very similar one that received its very first images.
This is an image of Europe as you've never seen it before. Captured in March 2023, it shows in great details much of a continent blanketed in clouds, with relatively clear skies over Italy and the Balkans. Hovering some 36,000 kilometers above our heads, the new MTG I1 satellite produces images of a full Earth disk every 10 minutes. This is what 24 hours of data reveals of Europe. The high resolution of his images is truly groundbreaking, helping our local weather forecasters to better predict where this approaching storm is headed.
We are almost finished, but here are some other news in brief.
On 1st of July, the Euclid spacecraft finally lifted off from Florida on a SpaceX Falcon 9 rocket. Once positioned some 1.5 million kilometers away from Earth, the Euclid telescope will observe billions of galaxies to create the largest, most accurate 3D map of the universe.
The hundreds of missions that will launch to the moon over the next decade and beyond will need technological support to help them navigate and communicate with Earth. ESA is now inviting companies in Europe and Canada to provide these services by putting a constellation of satellites around the moon. The initiative, called Moonlight, will also benefit the future permanent base due to be built on the lunar South Pole, the Lunar Gateway.
And that's it from us, from all the Web TV team. Thanks for watching.
And to keep up to date with space news, visit the ESA website and follow us on social media.
Goodbye.
Here I am in Tash in Switzerland, and this is where my adventure starts. We want to witness and analyze how the Gorner Glacier is shrinking. And why would an astronaut be going on an expedition like this? What does an astronaut have to do with a glacier? Well, it just so happened that when I was in orbit on the ISS, I took many pictures. And over the arc of about 6 years, from the first mission to the second, I saw with my own eyes the glacier slowly disappearing. It struck me. And so this group of scientists and climatologists asked me to come here and see it with my own eyes on the ground, what I'd seen from space. Then the helicopter starts flying sideways. Because the team blades are not in a natural configuration, because they rotate like this, the helicopter wants to fly. Frank, I'm here for the very first time, and it is a very unique environment to be.
Certainly.
And a very unusual one for an astronaut. Tell me a little bit, what am I looking at?
We're here in the beautiful Zermatt region. We are surrounded by the highest mountains we have in Switzerland. So it's actually the peak behind us is the highest mountain in Switzerland, and we have these beautiful glaciers.
Glaciers are living things. They change. They change with time. They change with climate, and they change with meteorological conditions as well. What is the story that the Gorner is going to tell us in the next couple of days?
Here we are in a very special place because all glaciers are composed of compressed snow, so this is not frozen water. And the snow that is the source of this glacier comes from the highest elevations up there at Dufourspitze. And at this elevation it is so cold that there's basically no melt all over the year, which means that the snow by the layers from further years is compacted more and more without melting. We name this somehow a dry recrystallization, which is the same process as in Greenland, for example. Okay. And this does only take place here and has this special, consequence that a part of the ice that we see down there at Gorner Glacier is so-called cold ice. So it is below 0 degrees. It appears also very white. Here in this case The white ice is also a little bit self-protecting because it is so bright. It reflects more of the sunlight, so that in the end the melt should not be so strong as for the darker grayer ice. And here this glacier, or this central part of the glacier with the cold ice, is really unique and the core of many studies.
One of the things that meteorologists and geophysicists study is also the ongoing changes in global climate. Is it something that is affecting this glacier as well?
Yeah, the global increase in temperatures is affecting,
global warming.
Is affecting all glaciers all over the world in exactly the same way. Thanks to the satellite data, a recently published study has shown that this meltdown of the glaciers is really all over the world. So, and it has also accelerated all over the world. And this is a little bit, let's say, the worst side of it, because glaciers adjust to the climate by changing their size.
Safer in my life, I'll tell you. It is a truly humbling experience to be up here in the beautiful setting of the Swiss Alps. I've only seen these images from space. I have taken many pictures of these locations and what is happening here, and to actually see with my own eyes and feel under my feet the rocks of the Swiss Alps, it's amazing. It's almost unbelievable. And now I've been up for 12 hours. I have eaten a couple of granola bars during the day. I've hiked for 5 hours, so I'm hungry and I'm ready to go. looked at a couple of things. First, we found Mulan. It's a shaft where melt water converges from river systems that are formed by the melting of the glacier, and then they go into the ice and melt it, creating this shaft. And the images are amazing. It's beautiful, although it is a sign of something terrible happening. Again, the melt of the glacier. And then once it goes underneath the glacier, it just flows towards the valley.
Qua dietro abbiamo un idrotticoio che prende il nome, come hai detto tu, mulino. Ve ne sono tanti sul ghiacciaio e ti posso dire che il numero sta aumentando e soprattutto la quantità di acqua. Adesso stiamo vedendo una vedière, cioè questo ruscello prende il nome di vedière, che è molto piccolo, ma in realtà ce ne sono tantissime e sono diffuse in tutto il ghiacciaio. Questo ci dice che la maggior parte dell'acqua di fusione poi finisce nel cuore del ghiacciaio e da qualche parte trova una via per fluire verso valle.
For monitoring glaciers, we use different tools, and that depends very much on the scale that we are monitoring. For example, we do assessment of glacier changes all across the Earth, and they are very much focused or based on remote sensing observations. So satellites that look at Earth either visually, so with pictures, or through radar, or through altimeters, so a range of tools. For the monitoring of Swiss glaciers, we also have in situ observations, so measurements that are done at the very site. What you're holding there, it's what we call an ablation pole, an ablation stick. So it's a device, it's maybe a bit exaggerated, but it's a pole that will stick in the ice with drill, and we'll use that to tell how much the glacier is melting. And well, if you want, you could do the job yourself, and I will show you. So I'm sure you know how to operate the drill. Just make sure when you start, make a little hole on it, and then try to have it as straight as possible, otherwise it will bend. And while
I'll do my best. I've never drilled a hole in the ice, but
try to exactly hold the hand there. That will give you control. And whilst you're going down, come up a bit. Yeah, exactly, so that you get rid of this pieces of ice that we are drilling through. That's it.
Okay.
And now
put this one down, or you want to hold it?
We can put that away. But yeah, you can get the ablation tool again.
Okay, so the ablation is just a scientific word for melting.
Yeah, correctly. So what we distinguish in the glacier cases is ablation, so the process that remove mass from the glacier, and here the main process is the melt.
Okay.
And accumulation, that would be the process by which we add mass to the melt.
So when it snows and it covers everything with snow,
exactly.
And then eventually that pressure from the snow will create new ice.
That's correct, yeah. This is something that doesn't happen in this very place, because here we are in what we call the ablation zone. So it's the zone on the glacier where we lose more ice to melt during summer that we can add to snowfall during winter. Whilst higher up, so in the regions that we see up there, there we are in the accumulation zone. So there we gain more snow during the year than we can lose during summer through melt.
So this is an important part that really explains the dynamic of a glacier. So let's say that again in common words that even an astronaut can understand. So basically this is like a river. It's flowing down from the place up there in the mountains where during winter it snows, it accumulates, it creates a lot of ice, and then eventually flows out down here. Here we don't really get more ice. We just get whatever it's coming down from the mountain. And during the summer, we get this ablation process, which is the melting of the ice, that creates a lot of water, rivers that go down to the valley.
You got it.
Did I say it pretty much okay?
Yeah, exactly.
Excellent.
And this flow is what is happening there is the ice deforming underneath its own weight. So you can imagine like a slab where you would put some honey on it, this will kind of make its way down. And the glacier here is the camera that will place to look at this very spot.
Okay.
And during the day, while the melt is happening, this will lower. And so what you will see is basically this ring sliding down the way.
Okay.
And well, in a bright day like this, at this elevation, we may see like 5 to 10 centimeters, so something like of melt. So when you come back in the evening, well, basically we are not walking over the same ice again because it will have molten by then already.
So this all part of the glacier is melting at the same speed, and that's about 10 centimeters a day on a hot day.
On a very hot day, yeah.
On a very hot day. So let's say 5 to 10 centimeters per day on average over the summer. So how much of this will have melted compared to from the beginning of the season to the end? How much ice will we have lost?
At the place where we stand, I would guess 3 meters.
3 meters.
So that's putting myself on top of your shoulders. That's more or less what if I sit on you. That's the amount of ice we lose every year here.
Every year we lose 3 meters of ice. Now, this is the question that's been burning me. Will we recover any of that in the next year, in the next winter? Will we recover any of that ice?
Well, unfortunately not, because indeed during winter we will have snowfall here. So when we are here in winter, you may have like up to 4 meters of snow. But this will go and melt away again at the next year. So we'll find the ice that will leave during winter. We have a bit of new ice coming in. That's the one flowing down the mountain. But in that time, the stake will have moved. So the ice that falls down is kind of pushing our stake away. And so the answer to your question is basically no. Unfortunately, we won't grow the glacier during winter.
There are 3 stark issues that are associated with glacier retreat. So on the one hand, we have a change in the hydrological system. So we get a lot of runoff. There are lakes that build in front of our mountain glaciers. And these can cause hazards. So there can be dams that break and flash flooding that happens. So we have also an increase in hazards in the mountain areas. When there is less ice, the mountain also the forces are differently distributed on the mountain. So we may have more rock falls, and the hazard zones are actually expanding. Then we also have the issue that when we lose ice, it flows into the ocean, and glaciers actually contribute to global mean sea level rise, and they contribute quite a lot. So from a climate perspective, that is a worrying aspect as well.
There is a system of caves. They are contact caves. It means that the glacier is touching the rock, and then the water plus the hot air from the outside mix together to create these incredible structures that are underneath the glacier. Unfortunately, despite their beauty, this also means that the roof of the glacier is getting thinner because of the hot air, and it is another sign that a few years from now, what I'm looking at today will not exist anymore. Probably next year, the cave that I was in will not be there. The roof of the glacier will be so thin that it will collapse, and then when I was standing under the ice, it will be just bare rock.
Fenomeni come questi stanno accelerando, cioè l'acqua che arriva da di lato sta entrando sotto il ghiacciaio e sta creando dei vuoti, ma siccome ci sono più ingressi c'è una circolazione d'aria e di conseguenza hai acqua più aria, quindi la fusione è aumentata anche con la circolazione d'aria. Ecco perché sta accelerando tutto questo processo.
So we're looking at different aspects of a glacier, for example, with different sensors that can give us different parameters of this particular natural phenomena that we're actually looking at. So that's actually quite interesting, and we need to have long-term data series.
Here we are at the FEE Experience. It's the place in the European Space Agency Center in Rome, the Center for Earth Observation, where we display the work we do with satellites. And here you see the Arctic sea ice extent, and the Arctic extent, as you can see here, is monitored via satellites day and night, via radar instruments and via altimeters. And this is over the 40 years of time that we have data, and normally we look at the lowest extent of the ice, which is in September. And in September, this is the time where you have a real reduction of the ice mass over the Arctic. And we do plan to have, by 2050, unfortunately, an ice-free Arctic during the summertime. We do look at sea level rise since over 30 years with national, European, American missions. And we look at the trend of the sea level rise. Sea level rise, which is due to, of course, temperature increase, but also ice melting all over the world. We see the variability of such sea level rise, which is not homogeneous, and we see that the trend is passing from an average yearly of 3.2 millimeters to 4.8 millimeters per year increase in the sea level rise. Here we look at Sentinel-5P data, greenhouse gases data. Nitrogen dioxide over Europe, but this is a satellite that passes every day over all of the world, and we see the variability between week and weekends. So the difference is very relevant. It's due to traffic reduction and reduction in industrial activities. So satellites help us in climate change to monitor greenhouse gases, to monitor CO2, methane, nitrogen dioxide, and help us supporting the climate crisis.
We are sort of thinking about the whole food chain, from producing the data and building the satellite and developing new technology and addressing new science questions, to actually putting these satellites in space and then using these data, and when they've flown long enough, we are able to actually construct long-term series of climate-relevant data. So we're using different sources, not only ESA, but mainly to create climate data records, we call. And these are relevant data sets that tell us something on how the climate is actually changing over decades and even longer. And you know, with the onset of satellite data 40 plus years ago, we now really have quite some long data sets that go sometimes beyond 30, 40 years really from space, which is a very exciting source of data.
Now, with your experience in climate, do you think that this is something that we can stop, or even better reverse, or is it something that you just hope?
I think if we are managing to limit the global warming to a particular degree, then we will probably be able to at least hold the status quo that we have at the moment. But you know, it's a very difficult question. It's the sort of $1,000,000 question, so to say. So I can't really answer that with a yes or a straight no or something like this. You know, I hope we will, and we have seen that with many countries that they're really starting to address it. So, you know, actually, I think we don't really have a choice. We have to limit our emissions. If we don't do that, then the destroying of our natural environment will continue.
I think it's quite iconically known that glaciers are melting, and it's all associated with climate change. We know this. I mean, we see it. If we go into the Alps ourselves, we can see the signs, the markings where the glacier was over the past decade. Satellites actually show us this globally. So it is actually a very recent development now with this program as well, that we have been able to monitor our glaciers globally from space over a long period. And what we see is that there is a global nature of retreat of these glaciers, and this is unprecedented, and in fact it's very worrying.
If we now really manage to put effort in abating emissions, we will be able to save, say, at least 40% of the ice. So half of this place is gone anyway, but still there will be something that we can look at and that we can show to our children, and that our children can show to our grandchildren.
I think nature is sending here a very strong signal to us.
I feel a little bit of urgency, and because it's me, I also feel hope that people will listen and understand the urgency of what is happening and how fast we have to react before everything that we have will disappear. So there is a lot at stake, and that is why this is now the time to act. Come on, buddy. I don't want to be rude, but you gotta get going. Okay.
What lady would take mathematics instead of Latin?
Nancy Roman has lived an extraordinary life. A talented astronomer, NASA's first chief of astronomy, and a lifelong champion of women in science. She even became the mother of the Hubble Space Telescope. Nancy Grace Roman was born in 1925 in Nashville, Tennessee, the only daughter of a music teacher and a geophysicist. Though her father was a physicist, it was Roman's mother who awakened her interest in astronomy.
I've been interested in it as long as I can remember. I blamed my mother because she used to take me out and show me the constellations and show me the northern lights and things like that.
This early appreciation of the night sky sparked a lifelong passion. By the age of 11, Nancy Roman had already formed an astronomy club and began to study astronomy on her own.
I think I've always been curious, and I just wanted to satisfy my curiosity. Astronomy in particular was a subject I wanted to learn more about.
Nancy followed her dream and became a professional astronomer, working in the new discipline of radio astronomy. And in 1961, she became the first chief of astronomy in the Office of Space Science at NASA, the first woman to hold an executive position in the agency. At NASA, Nancy Roman was instrumental in developing the first space observatories and in paving the way for the most famous orbital observatory of all, the Hubble Space Telescope. Other scientists had proposed a large space telescope, But it was Nancy who made it happen. She brought together astronomers, NASA engineers, and the cutting-edge technology.
And engineers and scientists don't talk exactly the same language. They have a different job. Astronomers, well, scientists in general are trying to understand why. Engineers are trying to understand how. And I found myself actually acting somewhat as an interpreter between them.
She united not only scientists and engineers, but also those who would fund Hubble. Nancy was able to convince politicians that NASA and ESA should join forces and work together to realize a large space telescope. On the 24th of April 1990, the NASA-ESA Hubble Space Telescope was sent into orbit above the Space Shuttle Discovery, the first space telescope of its kind. It offered a new view of the universe and has, for 30 years, surpassed all expectations, beaming back data and images that have changed scientists' understanding of the universe and the public's perception of it. Hubble's discoveries have revolutionized nearly all areas of current astronomical research, from planetary science to cosmology, and its pictures are unmistakably out of this world. This video will reveal some of Hubble's biggest science discoveries throughout its 3 decades of operation. An early and memorable result is the Hubble Deep Fields. These are extended observations of a particular region of the sky intended to reveal faint objects by collecting the light from them for an appropriately long time. These images fascinated scientists and the general public alike, as the thousands of galaxies captured in single images spawned widespread fascination and amazement. The original and now famous Hubble Deep Field image, released in 1996, consisted of an area of sky with a width equal to just 1/12 that of the full moon. In it, Hubble found almost 3,000 distant galaxies. The Hubble Ultra Deep Field from 2004 was the deepest portrait of the visible universe ever achieved by humankind. The 2012 Hubble Extreme Deep Field was an impressive combination of many existing exposures, over 2,000 of them, into one image. The results were astonishing for astronomers. By studying the thousands of galaxies captured in these deep field observations, including some of the most distant primeval galaxies, they were learning more about the very early universe. The bulk of the early and remote galaxies had not yet had time to form stars, and were also characterized by an atypical shape, as they seemed to be smaller and more irregular than those nearer to us. This was taken as a clear indication that galaxies form by merging together smaller objects. The Hubble Frontier Fields Observing Campaign drew upon the power of massive clusters of galaxies to unleash the full potential of the Hubble Space Telescope. Hubble's sensitivity and high resolution allow it to see faint and distant gravitational lenses that are harder to detect with ground-based telescopes. Gravitational lensing is a phenomenon created by extremely concentrated masses, like the cores of galaxies of galaxy clusters. Their strong gravity warps the surrounding space, and light from distant objects traveling through that warped space is curved away from its straight-line path, as if passing through a lens. Hubble can resolve details within the multiple banana-shaped arcs that are one of the main results of gravitational lensing, as the images of background sources are distorted. An important consequence of lensing distortion is magnification, allowing us to observe objects that would otherwise be too far away and too faint to be seen. Hubble makes use of this magnification effect to study beyond the sensitivity of its 2.4-meter diameter primary mirror, by showing us the most distant galaxies humanity has ever encountered. Hubble's observations of lensing effects have also given us a glimpse of the cosmos that will be unveiled by the upcoming NASA ESA CSA James Webb Space Telescope. One of Hubble's initial core purposes was to determine the rate of expansion of the universe, known to astronomers as the Hubble constant. This value is an essential ingredient needed to determine the age, size, and fate of the cosmos. Before Hubble was launched, the value of the Hubble constant was not known precisely, and calculations of the universe's age ranged from 10 billion to 20 billion years. Now, astronomers using the Hubble Space Telescope's data and observations have refined their estimates of the universe's present expansion rate and are working to make it more accurate. Hubble's refined distance values have helped to put the age of the universe at 13.8 billion years. While improving the measurements of the Hubble constant, the Hubble Space Telescope's data have also supported the development and use of the cosmic distance ladder, which is an important scientific tool that is used to measure accurate distances to galaxies near to and far from Earth. To do this, astronomers use Hubble to measure the distances to a class of pulsating stars called Cepheid variables, which are used as milepost markers. Once the Cepheids are calibrated, astronomers move beyond our Milky Way to nearby galaxies for other reliable yardsticks. Supernovae, exploding stars that flare with the same amount of brightness. Astronomers use the Cepheids to calibrate the relationship between absolute luminosity and apparent brightness relation for supernovae, which is a function of the distance from us of their host galaxy. We detect supernovae in galaxies hundreds of millions of light-years from us, giving us a powerful tool for calibrating redshifts at larger distances than Cepheids can. However, scientists discovered that supernovae at higher redshifts were fainter than one would expect when assuming a constant expansion of the universe, meaning they were further away. These observations helped astronomers to then determine how fast the universe is expanding over time. To their surprise, the data implied that the universe has not been expanding at a constant rate, but instead is accelerating. Many scientists believe this acceleration is caused by something called dark energy that must make up about 70% of the entire universe. By observing how dark energy behaves over time, astronomers hope to gain a better understanding of what it is and how it might affect the future of the cosmos. The telescope also carried out surveys and developed new methods to look for clues about the equally mysterious dark matter, which makes up about 27% of the universe. Astronomers used Hubble to create a map of everyday visible matter, from which they could trace the large-scale distribution of dark matter by studying how its gravitational presence distorted light in the images. Hubble has also lifted the veil surrounding the cosmic monsters that lurk at the center of most galaxies, supermassive black holes. Using its spectroscopic observing capabilities, Hubble peered into the galaxy cores and found that the stars there moved in tight orbits at enormous velocities. This strange behavior indicated the presence of a truly colossal gravitational field that could only be produced by a supermassive black hole. Hubble provided the first solid proof of their existence. Today, it is known that there is a black hole in the center of almost every galaxy. Another phenomenon that Hubble's instruments have observed throughout the years is quasars. These are powerful jets of energy that come from extremely luminous galactic centers. The power from a quasar is enormous, and they typically have luminosities thousands of times brighter than the Milky Way. In 1996, Hubble's 100,000th exposure was a quasar located 9 billion light-years from Earth. More recently, Hubble discovered the brightest quasar ever seen in the early universe. Hubble has revolutionized planetary science in a number of ways through its precise observations of our own solar system. Hubble has charted the dynamic activity on Jupiter and its moon Io. In 1994, it also witnessed a comet crash into the planet's surface. Hubble has also observed the auroras on several of our solar system's planets. Including 2013, Hubble provided the first observational evidence of water vapor erupting from the frigid surface of Jupiter's moon Europa, near its south pole. The telescope has also captured observations of some special interstellar visitors. In 2018, Hubble studied Oumuamua, the first interstellar object discovered in the solar system. In cooperation with other ground-based telescopes, it was determined that the object was likely a comet and was moving away from the Sun faster than previously expected. In 2019, Hubble provided astronomers with their sharpest and best observation to date of the interstellar visitor comet 2I Borisov, which is believed to have arrived here from another planetary system elsewhere in our galaxy. Hubble's high resolving power has also been crucial in the investigation of regions of star formation, both in the Milky Way and in other galaxies, and its infrared capabilities have allowed it to peer through the thick clouds of dust and gas present in those regions. The death of a star can be as beautiful and interesting as its birth. Hubble has observed both sun-like stars as they come to the end of their lives in the form of planetary nebulae, and massive stars experiencing explosive deaths as supernovae. By studying them at different times in their lives, Hubble has allowed us to paint a more complete picture of stars, the building blocks of galaxies. While not one of its original science goals, Hubble has also made a name for itself as an exoplanet explorer. In particular, by studying exoplanet atmospheres. The chemical makeup of a planet's atmosphere leaves a unique fingerprint on the starlight that passes through it. By studying the Orion Nebula, Hubble made the stunning discovery that at least half of the stars in the region were surrounded by rotating disks of gas and dust. The raw materials necessary for the formation of planets. In 2016, Hubble analyzed for the first time the dry atmosphere of a super-Earth 40 light-years away. In 2019, in an exciting discovery, the telescope's data were used to detect water vapor in the atmosphere of a super-Earth within the habitable zone. K2-18b is 8 times the mass of Earth and, at its discovery, was the only planet orbiting a star outside the solar system, or exoplanet known to have both water and temperatures that could support life. Prior to Hubble's work, just one planetary system had ever been confirmed. Hubble's observations have shown us that planets are being formed around many more stars than previously thought, increasing the possibility that life could exist somewhere out there. And in the future, Hubble could possibly find hints of life in one of these fingerprints. An outstanding, successful project of international cooperation between NASA and ESA, the Hubble Space Telescope will continue to work for as long as its components operate and it provides a good service to the scientific community. Its unprecedented capabilities have made it one of the most powerful science instruments ever conceived by humans, and certainly the one most embraced by the public. On its 30th birthday, we look back at its unparalleled scientific contributions and its spectacular imagery, while anxiously awaiting what discoveries are yet to come.